Hello, everybody. I am Anis Rahman, founder and CTO of Applied Research in Photonics in Harrisburg, Pennsylvania. I am here talking today about terahertz subsurface imaging applications for nanomaterials and soft tissue. Um, Please feel free to get back to us for any question and comments at the email info@arphotonics.net. The motivation of using terahertz is that it is non-destructive, non-contact, and we can do layer by layer imaging and analysis. We have achieved a resolution of 1 nanometer, which is very useful for semiconductor applications. And as I mentioned, it is non-destructive and non-contact. Spectral analysis can be done as well, and it is good for characterizing 2D and 3D nanomaterials as well as soft tissue. Soft tissue, because it is non-ionizing. The mechanism that we use for generation of terahertz is what we call is a dendrimer dipole excitation. Details has been published, but it gives us a way of getting continuous wave at wide broadband terahertz radiation. It can also be pulsed, but it allows us multispectral imaging very convenient way. So this is the setup on the left top corner, and we demonstrated it to a group of students and scientists, and we also have a live demo at booth number 734. Please feel free to stop by. The image here is showing the 3D nanoscanner. Is a 4-axis scanning, X, Y, Z, and theta. And the sample can be stationary, but sample can also be scanning. So there are two configurations. And beam delivery is by a fiber optic, therefore the sample can be versatile. You can just about any kind of sample can be scanned with it. The reproducibility of the scan is very good. And then the resolution, as shown here, the chromium nanoparticles, that we have achieved a resolution of less than 1 nanometer. So with that, let me show you an example of semiconductor imaging. In the semiconductor industry, the critical need is to be able to resolve small defects on the order of 1 nanometer, because their feature size is now going to be in the 10 nanometer or so. So this example shows that the stacking fault that we have analyzed with terahertz. The left sketch of the sample is that silicon, germanium buffer on silicon wafer, and then the second sample has the on top of the germanium buffer they have a CG layer, silicon germanium layer. On the right there is an example how the stacking fault looks like by TEM from IBM, and on the bottom is the TEM of the actual TEM image of the actual samples that we have analyzed. It shows the CG layer or silicon germanium layer has a thickness about 18 nanometer, and germanium layer has about 600 nanometer. Here's the 3D image that we have generated with our terahertz scanner. On the left is the germanium layer on silicon. On the right, germanium layer on silicon, and on top of that is silicon germanium layer. So we see that the silicon germanium layer in our measurement gave us a thickness of about 20 nanometer, but we also have seen that it varies between 15 and 20 nanometer, while the TEM data shows 18 nanometer, so this is in a good agreement. And, and we have measured the thickness of the germanium layer about 600 nanometer, which is in good agreement with the TEM data. Here is another example of imaging quantum dot samples. The quantum dot with TEM was found to be 11 plus minus 4.5 nanometer. In our measurement, only one quantum dot has a size parameter of 7.7 nanometer, so which is in the range of what the TEM has given. We did not do the statistical analysis. Doing statistical might improve the agreement. Here is a last example that I'm showing here is a 3D image of skin. On the left side, the skin as a soft tissue has the regular cellular arrangement. On the right side, so the left side one is the healthy skin, the right side one is the skin with basal cell carcinoma, and that shows that the cell structure has deteriorated, no regular cell pattern is on the onset of tumor formation. So with that, let me conclude that the terahertz imaging can achieve very high resolution of about 1 nanometer. It can image semiconductors, nanomaterials, as well as soft tissue like skin, but it can be applied to any other soft tissue. So it's a pretty versatile instrument. And we invite you to collaborate with us, as well as we offer contract services. So please send your sample to us for proof of concept or long-term contract services. With that, I thank you for your attention. Please get back to us at email info@arphotonics.org, or you can give me a call at 717-623-8201. And I thank you for your attention.